Welcome to the deep dive.
Good to be here.
Today we're really jumping into a core computer science problem.
The subset sum problem. Yeah, it's a classic.
We've been looking at some, well, really excellent explanations on how to tackle this using backtracking.
It's a great way to illustrate the technique.
And our mission really for this deep dive is to unpack it all, make it super clear so you listening get a solid understanding that, actually lasts.
Absolutely, because subset sum, it sounds simple on the surface.
Right. Given some numbers, find combinations that add up to a target sum. Easy.
But the details matter. Like, can you reuse numbers? Are there duplicates in the input set to begin with?
Those are the nuances the source material gets into.
Exactly. And they change how you approach it.
Which brings us to backtracking. That's the main tool we're looking at today.
It is. Backtracking is, it's a really methodical way to explore possibilities.
How does it work, basically?
Imagine you're building a solution piece by piece, maybe adding numbers to a list. If you hit a point where you realize, okay, this path I'm on definitely won't work, maybe the sum's already too high.
Right.
You backtrack. You undo that last step, that last choice, and try something different.
So you don't waste time going down dead ends.
Precisely. It's about searching smarter, not just harder.
Okay, let's nail down the basic subset sum idea. Example time.
Sure. Let's use the one from the material. Set is 3, 4, 5, and the target sum is 9.
Okay. 3, 4, 5, target 9. What combinations work?
Well, you could have 3, 3, 3. That adds up to 9.
Right.
Or you could have 4, 5. That also adds up to 9.
And importantly, as the source points out, we're talking combinations.
Yes. Order doesn't matter in the final result.
So 4, 5 is the same answer as 5, 4. It's just about which numbers are in the set.
Exactly. And for this discussion, we're dealing with positive integers for both the input numbers and the target.
Keeps things focused. Okay, so how does backtracking find 3, 3, 3, and 4, 5 without just, guessing?
Let's look at the first case they describe. Case 1. The input set, say our 3, 4, 5, has no duplicates inside it.
Okay, unique numbers in the input.
But you can reuse elements multiple times to hit the target.
Ah, so that's how we get 3, 3, 3. We reuse the 3.
Exactly. So the naive backtracking starts simple. You have an empty list, your potential subset.
Right, start from scratch.
At each step, you look at the numbers in your input set 3, 4, 5 and decide which one to add to your current list.
And you do this recursively.
Yes. You build it up, and you need to keep track of, well, two main things.
Sure.
The subset you're currently building. Let's call it current subset.
Okay.
And the sum of the numbers in that current subset so far. Let's call it total.
Got it. Subset and its sum.
So the process, as the comments in the source code put it, is like attempt, proceed, retract.
Attempt, proceed, retract. Okay, break that down.
Attempt, make a choice. Add an element, say 3, to current subset. Update the total.
Okay, I chose 3.
Proceed. Move to the next step. Make a recursive call to try adding another number. Go deeper down the path.
Retract. When that recursive call eventually finishes, either finding a solution or hitting a dead end and returning, you undo the choice you made. Remove the 3 you added, subtract it from the total.
Ah, that's the backtrack part. Undoing the choice so you can try a different one.
Exactly. You have to revert the state so you can explore other branches of possibility, like trying 4 instead of 3 at that step.
And when do you know you've actually found an answer?
Simple. When your running total equals the target sum.
So if total hits 9 in our example.
Yep. You found a valid combination, you record it, maybe add it to a list of solutions.
But there's an obvious optimization, right? You mentioned it earlier.
Yes, basic pruning. If you're considering adding a number, say 5, and your current total is, 7.
Oh.
Adding 5 makes the total 12, which is already greater than our target of 9.
So there's no point continuing down that path. None at all. Any further numbers you add will only make it larger, so you prune that branch. You don't make the recursive call for that choice. You just stop exploring that specific option for this step.
Okay, let's try walking through 3, 4, 5, target 9 with this naive approach. It sounds like it might generate duplicates.
It absolutely will.
Let's see.
Let's see. Start empty, sum 0.
Try adding 3.
Current 3 total 3 recurse.
From 3, try adding 3 again.
Current 3 3 total 6 recurse.
From 3, 3, add 3.
Current 3 3 3 total 9 success. Recorded 3 3 3. Now backtrack.
Back to 3 3 total 6. What else can we add? Try 4.
Add 4. Current 3 3 4 total 10.
What are the 9? Prune. Don't recur.
Right. Backtrack. Try adding 5 to 3 3.
Total 6 plus 5 equals 7. Still too big. Prune.
Backtrack again. Now we're back at just 3. Total 3. We already tried adding 3. Let's try adding 4.
Okay. 3 4 total 7 recurse.
From 3 4 try adding 3.
Total 7 plus 3 equals 10. prune.
Try adding 4.
Total 7 plus 4, it was 11. Prune.
Total 7 plus 5 equals 12.
Prune.
Backtrack.
Back at 3, total 3. We tried 4, now try 5. 3, 5, total 8. Recurse.
From 3, 5, try adding 3. Total 11. Prune. Try 4. Total 12. Prune. Try. Total 13. Prune. Backtrack all the way.
Okay, lots of pruning. Back to the start. We tried starting with 3, now try starting with 4.
Empty set. Add 4. Current. 4. Total 4. Recurse.
From 4, try adding 3. Total 7. Recurse. Add 3. Total 10. Prune. Add 4. Total 11. Prune. Add 5. Total 12. Prune. Backtrack.
Back at 4. Total 4. We tried adding 3. Try adding 4.
4. Total 8. Recurse. Try adding 3. 11. Prune. Add 4. 12. Prune. Add 5. 13. Prune. Backtrack.
Back at 4. Total 4. We tried 3. Tried 4. Try adding 5.
4. 5. Total 9. Success. Record 4. 5. Backtrack.
Okay, now back to the very start. We tried starting with 3, starting with 4. Try starting with 5.
5. Total 5. Recurse.
From 5, try adding 3. Total 8. Recurse. Add 3.
11.
Prune. Add 4. 12. Prune. Add 5. 13. Prune. Backtrack. Back at 5. Total 5. Try adding 4.
Okay, so we found 3, 3, 3, 4, 5, and 5, 4. But wait.
There's the problem.
4, 5, and 5, 4 are the same subset. Our naive approach generated it twice because it considered the order of choosing 4 then 5 versus 5 then 4.
Exactly. The search tree has separate branches for those sequences, even if the final collection of numbers is identical.
And the source material rightly points out that trying to just filter these duplicates after you find everything, that's not great.
No, it's inefficient. Imagine if you had way more numbers or larger subsets. You could generate a massive number of permutations of the same few combinations. Comparing lists or sets to deduplicate is slow.
So we need to be smarter. We need to avoid generating these duplicates during the search.
That's the key optimization for this first case. Pruning not just for exceeding the target, but pruning to avoid duplicate combinations.
How do we do that, specifically for case I, where elements are reusable but the input has no duplicates?
The insight, like shown in figure 1311 in the source, is that the duplicates come from different choice orders, 4, 5 versus 5, 4. To prevent this, we enforce an order on the choices we make within a single combination. We decide that the numbers must be chosen in, say, a non-decreasing sequence based on their position in the original input array.
Okay, wait. Our input was 3, 4, 5. Let's say these are at indices 0, 1, 2.
Right.
So if I choose the element at index 1, the 4, the next choice I make for this specific combination must come from index 1 or index 2.
Exactly. It must be index I or greater, where I is the index of the element you just chose.
I can't go back and pick the 3 from index 0 after I've picked 4 from index 1.
Correct. This prevents the 5, 4 sequence if you've already explored paths starting with 4.
How do you implement that in the backtracking code?
You add a parameter to your recursive function. Let's call it start index.
Okay.
When you make the initial call, start index is 0. Inside the function, when you loop through your choices, the input numbers 3, 4, 5, you only consider elements from start index onwards. And here's the crucial part for case I. When you choose an element at index, say you choose 4 at index 1, the recursive call you make to add the next element gets it as its start index.
So the next choice must come from index 1 or later. If I chose 5 at index 2, the next choice must come from index 2 or later, which is just 5 foot again in this case.
Precisely. This ensures the indices of the chosen elements in any generated sequence are always non-decreasing. I1, I2, I2 equals I2M.
That's clever. It neatly eliminates the permutations without needing a separate check.
It does. And the source mentions a couple of related optimizations that work well with this.
Like what?
First, sort the input array nums. So 3, 4, 5 is already sorted. But if it were 5, 3, 4, you'd sort it first.
Why does sorting help? We're using indices now.
It enables an even better version of the sum exceeds target pruning we discussed.
Ah, pruning 1 in the source.
Yes. Because the array choice is sorted, if you're considering adding Choi Chessie, and you find that total plus Choi Chessie is greater than the target, you don't just skip Choi Chessie, you could actually break out of the loop that's trying different choices at this level.
Oh, because if Choi Chessie is too big and the array is sorted, then Choi Chessie plus 1, Choi Chessie plus 2, etc. will also be too big.
Guaranteed. So no point even checking them. You break the inner loop for this recursive step and backtrack immediately. Big efficiency gain.
Nice. Okay, sorting helps pruning. What else?
The other thing mentioned is more of an implementation style choice. Instead of passing total down and adding to it, you can pass the target down and subtract the chosen element's value from it in each recursive call.
Ah, so you start with target 9, choose 3, next call gets target 6. Choose 3 again, next call gets target 3, choose 3 again, next call gets target 0.
And finding a target of 0 becomes your success condition.
That seems cleaner, maybe? Less state to update back when you retract?
Potentially, yeah. It's just an alternative way to track the same constraint.
Okay, so recapping case I. No input duplicates, reusable elements. Sort the input. Use a start index in the recursion, passing it to the next call. Prune by breaking the loop if target choice says size 0, using the subtraction method.
That's the optimized approach. It finds unique combinations efficiently.
Right. Now let's shift gears. Case 2.
The second variation. This time, the input array can have duplicate elements.
Like maybe 4, 4, 5. Let's call them 4A and 4B just for
A
discussion.
good way to think about it. 4A, 4B, 5. Target is still 9.
And the other key difference, each element from the input array can only be used once in any given combination.
Exactly. You can use 4A or 4B, but not both in the same subset. And you can't use 4A twice, even if you could in case I.
Okay, this sounds trickier. What new problems arise?
The main new problem comes from those duplicate values in the input. Look at 4A, 4B, 5, and target 9.
Okay.
Our previous start index logic helped avoid permutations like 5, 4A if we already found 4A, 5. But what if we explore picking 4A first? We might proceed and eventually pick 5, giving us the subset 4, 5.
Right. Found 4A, 5.
Now, we backtrack. Later, at the very first decision point, instead of picking 4A, we might try picking 4B.
Okay.
And from there, we might again proceed and pick 5, giving us 4, 5 again.
Ah, the same subset 4, 5, but one came from using 4A and the other from using 4B. That's a duplicate result we need to avoid.
Exactly. This is the specific issue highlighted with figure 1313 in the source. The start index pruning alone isn't enough when the input itself has duplicates. It stops permutations, but not these duplicates arising from identical input elements.
So we need another pruning rule. Pruning 4, they call it.
Yes. And again, this relies on the input array being sorted. So 4A, 4B, 5 is sorted.
Okay.
The rule is, when you are inside the loop, deciding which element choice chassis to pick at the current step.
Yeah.
If the element you're currently considering, choice chassis, is the same as the previous element in the sorted input, choice chassis 1, and you are past the very first element allowed by your start index, meaning I start index.
Wait, why start index?
Because if I start index, it's the first time you're encountering this value, or block of identical values, in this particular decision step. You have to consider it at least once. But if I start index, it means you're looking at, say, 4B, after having already considered and decided not to branch off from, or maybe you did branch and came back, 4A in the same loop.
Okay. So if choice SE is the same as choice SE1 and I start index.
Then you continue. You skip choice SE.
Why?
Because any valid subset that could be formed, starting with this choice SE, like 4B, would be identical to a subset that could have been formed, starting with the previous identical element, choice SE1, i.e. 4A, at this same decision level. By skipping the later identical elements in the same loop iteration, you ensure you only explore the possibilities starting from the first occurrence of that value in the current range of choices.
Let me try to say that back. In the loop for choosing the next number, if I see a 4B right after another 4B, and I wasn't forced to start my loop at 4B, i.e. I start index, I skip 4B because any solution involving it here would be a duplicate of a solution I could have found using 4A just moments ago in the same loop.
You got it. That prevents generating both 4A5 and 4B5. You'd only generate the first one you encounter.
Clever. Okay, that handles duplicates in the input. But what about the use each element only once rule? How does that affect the start index?
Yes. Pruning 3. This is fundamental to case 2. In case I, when we picked choice chassis, the next recursive call started from I, allowing reuse of choice chassis or later elements.
Right.
But in case 2, once you use the element at index 1, that specific instance is gone. It cannot be used again anywhere down this particular path. So when you make the recursive call after choosing choice chassis, the start index for the next level of choices must be I plus 1.
Not I, but I plus 1. That forces the search to only consider elements after the one you just picked.
Exactly. That's how you enforce the use each input element at most once constraint within a single combination.
Makes total sense. And the other pruning 1. Breaking early if the sum exceeds the target because the array is sorted.
Still applies. Still very useful.
Yeah.
You sort the input, you use the target choice SE0 check to break the inner loop early.
Okay. So for case 2, input duplicates allowed, use elements only once.
Sort the input array first.
Then, in the recursive function, use the iStartIndex and choice SE = choice SE1 check to continue and skip duplicate branches from identical input values at the same decision level.
Yep.
Use the target choice SE0 check to break the inner choice loop early.
Crucial for efficiency.
And, most importantly for the use once rule, When making the recursive call after choosing choice SA, pass I+1 as the new start
That's
index.
the complete picture for case 2. You combine all those pruning strategies.
Let's quickly trace 4A, 4B5, target 9 with this. Sorted. 4, 4, 5.
Start empty, target 9, start index 0.
Loop I from 0. Try I equal 4A. Is I start index? No, 0, 0, 0 is false. Is target choices 0 or no? In a 4A equal. Choose 4A. Recurse with target 5. Start index 1.
Okay, now target 5, start index 1, loop I from 1. Try I1, 4B is I start index. Yes, 1 is false. Wait, 1 is not greater than 1. Let's recheck the condition. I start. Oh, right. The index I refers to the loop index, and the current call start is the pass parameter. So in the first call starts 0. Inside the loop, I starts at 0. We pick choices 0. The recursive call gets start I+1 and goes 1.
Right, so second level, target 5. Start 1. Loop I from 1.
Try I1, 4B is I start. No, 1 is not 1. Is target choice is 1. No, 5, 4, wheel 0. Choose 4B. Recursive target 1, start index 2.
Third level, target 1, start 2. Loop I from 2. Try I2, 5. Is I start? No. 2 is not 2. Is target choice is 2, 0. No. 1, 5 is 0. Pruning 1. Target choice is less than 0. Break this loop. Backtrack.
Back to second level. Target 5, start 1. We tried I1, 4B. Loop continues. Try I2, 5. Is I start here? Yes. 2, 1. Is choices 2. Choices 1. No. 5, 4. Is target choices 2, 0. No. 5, 5. 5 is 0. Choose 5. Recursive target 0. Start index 3.
Fourth level, target 0. Success. Record the path taken. 4A, 5. Backtrack.
Back to second level. Target 5, start 1. We tried I2. Loop ends. Backtrack.
Back to first level, target 9, start 0. We tried I0, 4A, loop continues. Try I1, 4B. Is I start? Yes, 1, 0. Is choices 1, choices 0. Yes, 4B equals 4A. Pruning 4 continues. Skip this choice.
See, we skipped considering 4B at the top level because we already considered 4A and they are identical. This prevents the 4B5 duplicate path.
Brilliant. Okay, loop continues. Try I2, 5. Is I start? Yes, 2, 0. Is choices 2 equals choices 1? No, 5 equals 4. Is target choices 2, 0? No, 9, 5. Choose 0. Choose 5. Recursive target 4. Start index 3.
Third level. Target 4, start 3. Loop I from 3. Array ends. Loop doesn't run. Backtrack.
Back to first level. We tried I2. Loop ends. We're done. The only solution found is 4 or 5.
And found efficiently without generating duplicates.
Wow. Okay, putting it all together, we've really dissected 2 common scenarios for subset sum.
And the key takeaway is how backtracking gives you this framework, this systematic exploration.
But the raw backtracking is often not enough.
Right. It's the pruning where the cleverness lies. Thinking carefully about why you're getting duplicates or why you're exploring pointless paths.
And then designing rules like the start index updates, the sorted array checks, the duplicate value skips to cut out that wasted effort.
Exactly. These aren't just minor code tweaks. They fundamentally change the efficiency and correctness of the algorithm. Understanding why each pruning rule works for its specific case, that's the deep understanding we were aiming for.
It feels like a transferable skill, this way of thinking, analyzing the search space, identifying redundancy, and actively pruning it.
It absolutely is. Subset sum is just a really clear example. This pattern of recursive exploration plus intelligent pruning comes up in countless combinatorial problems.
You learn these techniques for subset sum, and you really gain a powerful tool for your algorithmic thinking toolbox. It helps you see how to break down complexity.
Well said.
So, as we wrap up this deep dive, here's something to mull over. We saw how slight tweaks to the rules can you reuse items. Are there identical items in the source list? Demanded quite different pruning strategies.
Right, the algorithm had to adapt significantly.
How might this core idea, the need to precisely identify and account for sameness or reusability or other constraints when you're exploring possibilities, apply in fields totally outside programming? Think about planning projects or managing resources or even just brainstorming creative ideas. Where else does failing to account for these kinds of constraints lead to redundant effort or flawed outcomes?